In this video, we're going to study a topic in a lot more depth that we did touch on earlier in the quarter, and that is being able to graph quadratic functions. All right, so first of all, a quadratic function is one that has this form, ax squared plus bx plus c. But of course, the b or the c or both of them could be equal to zero. And so we're going to start with when that's the case, kind of the simplest quadratic function, which is f of x equals x squared. We call the graph of this quadratic function a parabola. And so here is f of x equals x squared. And you'll notice I've plotted seven kind of key points. And these key points are coming from me plugging in -3, -2, every integer all the way up to +3. And so, of course, if I square the negatives, they all become positive. And of course, the positives stay positive. So that's why a parabola has this behavior of on either side of x equals 0, um, it has the same y values because the negative x's get squared and become positives. And of course, the positive x's, when they're squared, are positive. All right. But some new terminology that we're going to look at here is, first of all, the vertex. So the vertex is, in this case, where the function bottoms out. This is the vertex. We'll see some examples later of parabolas that are facing downward. And so in that case, the vertex would be where the function reaches its maximum. So in this case, it's 0, 0 is the vertex. And then the axis of symmetry, well, you can see that, of course, the parabola is symmetric. And we'll just really emphasize this here. Symmetric about the line, x equals 0. So what's happening here is, oops, I grabbed the wrong thing here. X equals 0. That's our axis of symmetry. And that's just literally the line that you could fold the graph over and they would touch each other, right? They are perfectly symmetric about that line. All right. So a couple things to keep track of: vertex and axis of symmetry. So what we're going to do is we're going to plot some functions that kind of look similar to f of x equals x squared, but we'll have variations on them. And one of the things we're going to be interested in is what happens to the vertex as we do little variations on f of x equals x squared, and also what happens to the axis of symmetry. All right, so let's take a look at another one here. So g of x equals x squared plus 3. Well, if we go ahead and make our table of values, maybe we can go ahead and start at least by using the same x's that we did on the previous page. So if I plug in, oh, I'm sorry, if I plug in -3 is what I meant to write. If I plug in -3 and square it, but then I add 3, we know from the order of operations, we're going to square the -3 first and then add 3. So I end up with 12. -2 squared plus 3 would be 4 plus 3, which would give me 9. -1 squared plus 3. So I get 4. Three. And then one of the things that we can realize with parabolas is because we do have this perfect symmetry, that once you hit the vertex, which it looks like we have, then um, our graph in terms of the y values is doing the same thing on both sides of that vertex. So not surprisingly, when I plug in 2, it's doing the same thing as -2. I get 9. When I plug in 3, doing the same thing as -3, giving me 12. So I can plot all these points. So let's see, negative 312, that's going to take me off the grid. So maybe I'll start with negative 2, 9, which puts me right there. Negative 1, 4, puts me there. 0, 3, 1, 4, and 2, 9. So there's a sketch of my parabola. So what you can see here is that our vertex has not moved from what it was on the previous page in terms of the x value, but it has moved in terms of the y value. So 0, comma 3 is my vertex. But my axis of symmetry is still x equals 0. So when I had x squared and then I added 3, it did not change my axis of symmetry. So this is the x value I still found my vertex at. And so that's good information because now I know the exact same thing that's happening at negative 1, negative 2, and 3 is what's happening at positive 1, positive 2, and positive 3, respectively. So that'll make this next example easier. So this time the only difference is we are taking x squared and subtracting 4. But it really has the same flavor as that previous problem. So as I make my table, what I'm going to anticipate here to make life go a little bit quicker is I'm going to anticipate that just like on the last one, the axis of symmetry is still 0. I'm just going to go ahead and say that right now. X equals 0 is the axis of symmetry. And so as I make my table, I should still put x equals 0 kind of right in the middle. All right, so 0 squared minus 4 is negative 4, of course. And so here is my vertex. All right, and so let's go ahead and plug in 1, 2, and 3. So we get negative 3. So go over 1, down 3. So 4 minus 4 gives me 0. And 9 minus 4 gives me 5. But the fact that I've already identified x equals 0 as being my axis of symmetry means as I go equal amounts in the other direction, I can just copy the work that I already did, right? So because this was negative 3, 0, 5, this has got to be negative 3, 0, 5. And there's my graph. So in general, here's what we can say. If you are graphing something of the form f of x equals x squared plus k, and by the way, k can be positive or k can be negative. Okay. So like in this last one, we would say k is equal to negative 4 is what we'd say. So if k is positive, then the graph of f of x equals x squared plus k is going to have the same look as the graph y equals x squared, but it's going to be shifted up k units. Okay, so if I go all the way back to here, take a mental picture of this black graph. When I added 3, it's the same exact graph, just everything got moved up 3. And then here, everything got moved down 4. And so that's what the second one says. If k is negative, then the graph of f of x equals x squared plus k is y equals x squared shifted down k units. And the vertex is 0k, as we saw in those two examples. And the axis of symmetry, of course, is the y-axis, or if you could write it like this, x equals 0. All right, so now let's look at a different flavor. This time, instead of adding or subtracting outside of the x squared, we're going to add or subtract to the x before we actually do the squaring. All right. And we've actually done an example or two like this back in some of the earlier work that we did. So, um, if you recall, one of the things we wanted to do is we wanted to make sure that we could see, based on the points we chose to graph, we wanted to make sure that we could see where the function bottomed out. And so we kind of have some new language for that, is we want to make sure we, oops, make sure we graph on both sides of the vertex. So, in other words, don't stop picking different x values to try to sketch, um, or to try to find the points for and then sketch until you know you found the vertex. So at first here, this might require a little bit of trial and error. So let's just pick the same value that we started with in the previous tables. We started with -3. Let's do that for starters. So -3 minus 4 squared. Hmm. -7 squared is 49. Well, that isn't going to work very well in terms of being able to make an accurate sketch on this graph. So what I'm thinking is I'm not probably not going to bother with -2 either, because I think that's going to also give me a fairly large number that I'm going to have to square. So let's skip ahead a little bit. Now let's think about what would give me a nice small number to square. Well, the smallest I can think of is if I picked 4, right? If I put 4 minus 4 and squared it, of course, that gives me 0. So if I go over to x equals 4, y equals 0, there's one of my points. All right. In the interest of keeping the numbers that I'm squaring smaller, let's go on either side of 4. So 3 minus 4 squared. So 3, 1. And then 5 minus 4 squared is also going to give me 1. All right, let's go on either side of that. 2 and 6. So we get 2, 4. And then, oops, sorry, I graphed the wrong one there. I apologize. 2, 4. What I was doing is I was anticipating what's going to happen when I plug x equals 6 in there. So here's 2, 4. But that's exactly the same thing I get when I plug in x equals 6. Okay. Maybe we'll just do one more on either side. 1 minus 4 squared is -3 squared, which is 9. So yes, I can fit that onto my graph. Get the same thing when I plug in 7. All right, so there's my sketch. And so you can see that this time when I subtracted 4 from x before I squared it, that had the effect of moving the vertex over to 4, 0. And then it also changed the axis of symmetry, right? The axis of symmetry for this parabola is now x equals 4. But it didn't affect the y values at all. Okay. So in this case, the x value of our vertex ended up being the place where if you plug in that x value, you end up getting a 0 for the thing that you're going to end up squaring. Right? So we can maybe kind of anticipate what's going to happen here. So as I'm trying to make a sketch of this, and I'm thinking about the table I want to use, I'm going to go ahead and start with -2 as the first thing that I graph, because that will make the thing that I am trying to square equal to 0. So we end up right here. And then, like we did on the last one, let's go on either side of that. So negative 3 plus 2 squared. So negative 3, 1. Negative 1 plus 2 squared is 1 squared. Sorry, I'm just full of mistakes on these, full of typos. Equals 1 squared, which equals 1. And then go 2 in each direction. Right. And then we can probably make a pretty good guess as to what will happen at negative 5 and at 1. Get 9 for both of those. Right. So there's our parabola. And we can see right here the vertex is negative 2 comma 0. And then our axis of symmetry is x equals negative 2. Now, what I want you to notice here is that when we had x minus 4, that ended up putting the vertex at 4 comma 0. When I had x plus 2, it put the vertex at negative 2 comma 0. So to summarize here, if you have x minus h squared, then that moves your vertex to the right h units. Okay. And if uh, h is negative, then it moves it to the left h units. Now, at first that might seem a little strange, but let's use our previous example. It was x plus 2 squared, right? So if I do f of x equals x plus 2 squared, we know that one went to the left 2 units, right? Well, that's the same as x minus negative 2, right? So that makes sense, right? So if you have a minus sign here and h happens to be negative, minus a negative does turn into plus 2. However, a nice way to remember it is to just simply say this. When it comes to moving the vertex to the left and to the right, you go in the opposite direction of the symbol you see. So if you see plus 2, you're going to the left 2. When you see minus 4, you're going to the right 4. Okay, so that's probably the way that most people tend to prefer to remember it. All right, so one more thing that we want to be able to do is um, talk about what happens when we multiply our x squared by a number. So we're going to start by graphing f of x equals x squared. Now I can make a table of values for this. And actually, let's go ahead and make the table, but I'm going to not show a lot of detail. So f of x equals x squared. So here's my typical values that we like to sketch, or that we like to put in our table in order to sketch the graph. I'm just going to put the y values that we know we get. So make a sketch of this. All right. So now we're going to make a sketch of g of x is equal to 2x squared. So over here, make a table. And I'm going to go ahead and use the exact same x values so we can really compare the two. All right. So what's going to happen here, of course, is we are doing 2x squared. Well, remember that the order of operations is that you are going to square first and then multiply second. So it'll be 2 times 9 squaring first, and then that gives you 18, which is probably too big for our graph. So let's move on to the next one. Negative 2 squared is 4. So we get 8. Okay, well, I can graph that. So at negative 2, x equals negative 2, I'm at y equals 8. So 2 times, well, negative 1 squared is 1. So we get positive 2 when x equals negative 1. So it puts us right here. And then we're still at 0, 0. So that's the same. But again, I think we're getting symmetry here. So we'll be at 1, 2. And so you can bet we're also going to get 8 here and 18 here after doing the work. All right. So what happens here is when we multiply x squared by 2, we end up with a graph that looks like this. And so what it's done is it's multiplied all the y values of f of x equals x squared. It's multiplied by 2. We call this a vertical stretch. Okay, you can kind of imagine grabbing onto that black graph and then pulling up on it, stretching everything out. And that's how you arrive at the green graph. We can do a similar thing for the p of x function, though I'm not going to show nearly as much detail in doing so because notice all that's happening is I'm multiplying by negative 2 instead of positive 2. So I'm just going to do these 5 numbers and understand that all that's going to happen is I'm going to get the exact opposite of the numbers that I came up with over here as I made this graph carefully. So 0, 0, negative 1, negative 2, and positive 1, negative 2, and then left 2, down 8, right 2, down 8. So again, y values are multiplied by 2, but really multiplied by negative 2. So this flips the graph over. Okay. So um, anytime you have a negative out here, takes the original and flips it over the x-axis. Right. So that's what this is saying to us. Um, so if A is positive, the parabola opens upward, like in this one. If it's negative, then it opens downward, like in this one here. Oops. All right. And then if you're multiplying the A that you're multiplying the square term by is greater than 1, then it makes the parabola narrower or vertically stretches it. And if it happens to be less than 1, then it makes the parabola wider than the graph of y equals x squared. All right. So now putting all this together, right? What we can say is in general, if a quadratic function is written in this form, then you can actually tell a lot from it. If a is greater than 0, it opens upward. If it's less than 0, it opens downward. Get rid of that. Keep my color coding consistent. There you go. A greater than 0 opens upward. Less than 0 opens downward. And then the axis of symmetry is x is equal to h, and the vertex is h comma k. So you can just read it off directly from there. Okay, so this gives us kind of an alternative way of being able to quickly sketch a graph. So I'll show that here. All right, so it wants us to graph this. Now, while we could make a table of values, what I can do instead is I can first start by saying what my vertex is. Okay, so when it comes to the x and y values of your vertex, remember that the y value is exactly the same number that you see out here. So if you do +1, then that means the y value of your vertex is +1. If it was minus, then you would have a negative here in the y value. But for the x value of your vertex, which is in here, it's going to be the opposite. So when you see x plus 2, it actually means that there's a -2 as the x value of your vertex. And for that matter, x equals -2 is the axis of symmetry. All right. So I can put all that information right here. -2, 1, there's my vertex. Axis of symmetry, I can go ahead and pencil that in. And then because the number out front here is positive, we know that the parabola opens upward. So when we make our table of values, we can understand that we're going to work off of that axis of symmetry. So -2, since x equals -2 is our axis of symmetry, is where we want to have kind of at the center of our table. So I'll go 2 back in that direction, and I'll go at least 2 in this direction, and then we'll see what we get. So we have 2 times -4 plus 2 squared plus 1, which is 2 times -2 squared plus 1, which is going to be 2 times 4 plus 1, which is 9. So go over to -4 and then go up to 9. Do the same thing here. So we get 3. So -3, 3. And then the beauty of the axis of symmetry is that since I already know -2, 1 is my vertex, then on the other side of the vertex, I can just copy the work I did here, right? I can just put 3 and 9. Of course, if you did all the arithmetic, that's exactly what you would find. But that's exactly what the axis of symmetry does for us, is it gives us a quick way of finding points that I can use to sketch my graph.